In this session, we will learn the concept of homomorphic filtering, which is a generalized technique for signal and image processing. This concept was developed in the 1960s at MIT. Homomorphic filter is a kind of homomorphic system edge that passes the desired signal altered while removing the undesired signal. For example, X1n is the undesired signal. We can define the homomorphic system edge to convert X1n into a data function and pass through S2n directly. Then the output after the homomorphic system is just the desired signal X1n. For linear system, this is analogous to additive noise removal. Homomorphic filtering generally involves a nonlinear mapping to a different domain in which linear filter techniques are applied, followed by mapping back to the original domain. In speech analysis, for a windowed signal Xn, which is a convolutional combination of the excitation pulse En and the vocal tract impulse response Hn, linear function Ln is designed in different way to recover the vocal tract component Hm of the excitation pulses En. For example, in the computation of the spectrum as a sound representation, homomorphic filtering is used in the log spectral domain to separate filter effects from excitation effects. The goal is to separate out the excitation impulses from the remaining components of the complex spectrum and to use spectral window Ln to separate the excitation pulses from combined vocal tract. The filtered signal is processed by the inverse characteristic system to recover the combined vocal tract component. As is shown in the figure, homomorphic filtering is often used in the log spectrum domain, which can be interpreted as a linear smoothing of log x omega. Figure A shows the implementation of homomorphic filtering in frequency domain. Figure B shows the exploitation of the operation in Figure A. Figure C shows the kind of interpretation in frequency domain. Here, we introduce a new concept, lifter, L omega. Filtering means linear operation on time signal, while liftering means linear operation on spectrum. Homomorphic filtering can be viewed as the smoothing of the logarithm of the signal spectrum. Figure A is a harmonic spectrum. Figure B is the logarithm of a harmonic spectrum. Lifter L omega is used to smooth the log x omega. It is also regarded as logarithmic compression operator. The flowchart shows liftering in the frequency domain. The input signal passes through a series of operations and outputs the smoothing spectrum. If two signals are convolved, their Fourier transforms are multiplied, and a suitable defined complex logarithm will produce the sum of two log Fourier transforms. The inverse Fourier transform of a sum is the sum of the individual inverse transforms. So the cascade of Fourier transform, complex logarithm, inverse Fourier transform maps convolution into a sum of corresponding signals. Then, through designing linear system, we could get low frequency filter corresponding to low pass filter in spectral domain, and high frequency filter corresponding to high pass filter in spectral domain. Then, by means of Fourier transform and exponent function, a kind of homomorphic spectrum will be obtained. The figure shows homomorphic spectrum with low frequency filtering leading to the smoothing of the spectrum. We could get the envelope of the short-time spectrum with spectral filtering technique. Both homomorphic spectrum and LPCA spectrum can represent the envelope of the short-time spectrum. This figure shows the spectral smoothing effects of low-frequency spectral filtering on the log magnitude spectrum of a speech signal. This is done by first computing the real spectrum of a window-weighted frame of speech and saving the resulting log magnitude spectrum as the baseline and smooth speech spectrum. A low-frequency filter is then used to effectively smooth the log magnitude spectrum, with the cutoff frequency varies from a low value of 20 to a high value of 100 in steps of 20 frequencies. The most smoothing occurs with low cutoff frequencies for the filter. The least smoothing occurs with high cutoff frequencies for the filter. The figures show homomorphic filtering of voiced sound by real spectrum. Figure A is the window signal of voiced sound. Figure B is the logarithmic spectrum of the window signal. Figure C is impulse response of filter. Figure D is the smoothing logarithmic spectrum. Figure E is the windowed excitation signal. Figure F is the log spectrum of high frequency part of the spectrum. In the frequency domain, we can regard the speech signal as the product of the spectrum envelope and the details of the spectrum. The envelope part corresponds to the low frequency information of the frequency spectrum, and the detailed part corresponds to the high frequency information of the frequency spectrum. SRM analysis can convert the convolution relationship of the time domain signals corresponding to the two parts into a linear additive relationship. Thus, we only need to pass the spectrum through a low frequency filter to obtain the time domain signal corresponding to the envelope part, and pass high frequency filter to obtain the time domain signal corresponding to the detailed part of the spectrum. By use of a filtering technique, we could separate the sound source and the vocal tract easily. Here is an example of homomorphic filtering of voiced sound. Figure A shows the waveform, solid line, and aligned analysis window, dashed line. Figure B shows complex spectrum of windowed speech signal Sn, solid line, and low frequency filter dashed line. Figure C is log magnitude spectrum of Sn, thin solid, and of the impulse response estimate, thick solid. Figure D shows impulse response estimate from low frequency filtering. Figure E shows the spectral unwrapped phase of Sn, thin solid, and of the impulse response estimate, thick solid. The smooth estimate is displayed for clarity. Figure F shows the estimate of windowed impulse train source from high-frequency filtering. That's all for this session. See you next session.